Welcome back. All right, so today's lesson, section 4.4, is doing indeterminate forms of L'Hopital's rule. L'Hopital was a mathematician, and this is when we're doing a limit, and maybe your Calc 1 teacher alluded to this, but there's actually a way that you can kind of skip the hard stuff as you're doing limits, and this is the way to do that. And so L'Hopital's rule basically says that if the limit for both the numerator and denominator both go to 0, so this goes to 0 and this goes to 0, then we end up with, we're able to do is we're able to say that this is the same thing as x is approaching a of f prime of x over g prime of x. So now please note this is not the quotient rule. I just want to make that clear. This is literally the derivative of the function on top divided by the derivative of the function down below in the denominator. So this also holds true if either the numerator or denominator goes off to infinity. So we get the infinity over infinity or the 0 over 0. We can use L'Hopital. So if this goes to infinity plus or minus infinity and this goes to infinity, then we again can use L'Hopital's rule, f prime of x over g prime of x. This is a very handy rule. Makes things a lot easier. All right. So find the limit. Now, it has to be one of these two. It has to be 0 over 0 or infinity over infinity. And we can apply the rule numerous times if we need to, which is cool. So for part 1 here, limit as x approaches 1 of x cubed plus x squared minus 2x. Now, if I plug in 1s there, a 1 there, a 1 there, and a 1 there, that's going to be 2 minus 2, which is 0. And down here, that's also going to be 0. So we end up with the case 0 over 0. So we can apply L'Hopital's. If it wasn't 0 over 0 or infinity over infinity, we would not be able to apply L'Hopital's. So let's do it. I write a little h like this when I apply L'Hopital's. This is going to be 3x squared plus 2x minus 2 over 1. Now when I plug in 1, that's going to be 3 plus 2, that's 5. 5 minus 2 is 3. So this limit converges to 3. All right, let's take a look at this one. When I plug in 0 in the numerator, that gives me root 9. Root 9 is 3. 3 minus 3 is 0. And down here, I'm obviously going to get a 0. So this is, again, the 0 over 0 case. You have to check each time. You can't just start using L'Hopital's rule. So we do have the right form. So I'm going to apply the derivative. And remember, this is 9 plus 3x to the 1/2 power. So limit as x approaches 0, that's going to become 1/2 times 9 plus 3x to the negative 1/2 times 3. For chain rule, right? Because the chain rule in there. Divided by 1, which is nice. And let's rewrite this a little bit. All right, so I am going to plug in 0 here. I'm going to plug in 0, I get root 9. And root 9 is 3. It looks like this reduces to 1/2. All right, next part 3. Scooch that up a little. All right, so we plug in 0 there, we get a 1. 1 minus 1 is 0. And we plug in the 0 there, so that's 0 minus 0 over 0. So again, we have the 0 over 0 case. All right, so let's apply L'Hopital's. Derivative e to the x is e to the x. Derivative negative x is just 1. All right, so let's try plugging in the 0. I plug in the 0 here. I get e to the 0, which is 1 minus 1. That's 0 again. And down below, so again, I have the 0 over 0 case. So I'm going to apply L'Hopital's a second time. And now when I plug it in, I'm going to get e to the 0, which is 1/2. So in this case, we had to apply L'Hopital's twice. And let's do number 4 here. So it's a little hard to see. This is as x is approaching pi over 2 from the negative side. And that up top is going to give me infinity over infinity. Remember, there are asymptotes for both those functions at tangent and secant at pi over 2. So we can still apply L'Hopital's here, which is nice, because this is the other form that we can use, the infinity over infinity. So the limit x approaches pi over 2 from the negative side. And I'm going to apply L'Hopital's. I'm going to take the derivative. So that's going to be secant squared x over. If you remember, the derivative of secant is secant tangent. I'm going to reduce one of the secants here. So one's left up top, that one's gone. And let's play a little bit with our trigonometry. It's going to be secant x over tangent x. And I'm going to break that all the way down into the its sine and cosine components. Secant is 1 over cosine. Now tangent is sine over cosine, and so because it's in the denominator, we flip that. That's going to be cosine x over sine x. And so this gives us the limit as x approaches pi over 2. On the negative side, this is going to be 1 over sine x. Now here's the good news. Sine of pi over 2 is 1. So we end up with 1 over 1, which is 1. And number 5 here. So let's check to see which indeterminate case this is. If it is, sine of pi is 0. Now cosine of pi is -1. So this does not fall into L'Hopital's, but that's okay. This just tells us that the limit is 0. Easy enough. So that's L'Hopital's at face value. We're now going to step into the little bit more complicated ones, where we have other indeterminate forms. So we have 0 times infinity. And when we say indeterminate, it means we can't determine if it's convergent or not. It could be divergent, it could be convergent, we just don't know. Infinity minus infinity, we don't know what that is. Just at face value, we're going to have to explore that more. 1 to the infinity power, 0 to the 0 power, and infinity to the 0 power. These are all indeterminate cases where we just don't know enough to be able to do this. So let's start with 1 here, and we're going to have to do some algebra tricks to try to get it to be 0 over 0 or infinity over infinity. Again, those are the only two that are able to do. So we're going off to infinity here. This is x squared. So x squared, as x goes to infinity, that's going to be infinity. And as x goes to infinity down here in the denominator, that whole thing is going to 0. So that's going to be infinity times 0. So we're at this indeterminate form right now. And we can't apply L'Hopital's yet. We have to get it into infinity over infinity or 0 over 0. I know I keep repeating myself, but I want that to stick. So I'm going to do an algebra trick. And I'm going to bring that x squared down below, and it becomes 1 over x squared. Now I have 0 over 0. Now I can apply L'Hopital's rule. So let's do that. Derivative sine is cosine. Times, this becomes negative 1 over 2x cubed. And this is over negative 2 over 2x cubed, x cubed, pardon me. And we can see the x cubes go away. And we are left with a couple of negatives, it looks like. Now, here's the good news. As that goes to infinity there, that whole thing goes to 0, and cosine of 0 is 1. And that's going to be negative 1/2 over negative 2, which when we scrunch it all down, just becomes a positive 1/4. Partition that a little bit. All right, this is a little hard to see. This is as theta is going to pi over 2 from the negative side, from the left side, I should say. And please note, this is going to give us infinity minus infinity. So here's our next indeterminate form. But again, I'm going to rewrite this in such a way so that we end up with sine of theta over cosine theta minus 1 over cosine theta. And you'll note we already have a common denominator, which is nice. And we're going to make that into a single fraction. And now when we plug in pi over 2, oh, I lost the left side. Sine of pi over 2 is 1, 1 minus 1 is 0, and cosine of pi over 2 is 0. So we now have one that we can use L'Hopital's with. Derivative sine is cosine theta. Derivative cosine is negative sine theta. And this is now, when I just dump it in, this is going to give me 0 over negative 1, which is just 0. All right, these last three are a little insane. So you can see I have a lot of space ready for them. So in this case, I have 1 plus 1 over x to the x power as x approaches infinity. Now you'll note this is going to give me, as that goes to infinity, that whole part goes to 0, and that goes to infinity. This becomes 1 to the infinity power, and you'll look up here and see that that's one of our indeterminate cases. So I'm going to do an algebra trick. And you'll notice the E and the ln, they cancel each other out, and I'm back to where my original. But I'm going to leave it like this. And what I'm going to do is I'm going to use the limit, but I'm just going to focus on the exponent here. I'm going to do that actually for all three of these. So as sort of a separate problem, we'll come back to this. I'm going to do the limit only of this. And you can see with the ln that x comes down. And now I have infinity times 0, because that goes to 0 and natural log of 1 is 0. So infinity times 0. So now we're back to this type here, like this example. So I'm going to do another little trick here. This is ln of 1 plus 1 over x over, and I'm going to bring that to the denominator, kind of like I did with the first example. This is going to become 1 over x in the denominator. And now I have 0 over 0. As that goes to infinity, the whole part goes to 0. Ln of 1 is 0. And that, as x goes to infinity, that goes to 0. So now I have my 0 over 0. So now I'm going to apply L'Hopital's. This becomes 1 over 1 plus 1 over x times negative 1 over x squared over negative 1 over x squared. And you can see very nicely, those are gone. Which means this limit, as x goes to infinity there, that goes to 0, which means this limit goes to 1 over 1, which is 1. Now I'm not done. Remember, that's just the exponent here. So I'm going to go back to the original problem. And this becomes e to the first power, or just e. We are going to do a similar trick for these two. So let's see what we have here. We have 0 to the 0 power is what we're getting. So we're now to this indeterminate case. And I'm going to do the same trick I did over here. So this becomes the limit as x approaches 0 from the right side of e to the ln of x to the 2x. And like I did before, I'm going to just focus on that numerator, and then I'll come back to the bigger picture here. All right, and you'll note that I now have 0 times infinity, actually negative infinity. So we're almost there. So I got to manipulate this a little bit more. And I'm going to bring the 2 out there. This is ln x over 1 over x. And I'm going to apply, this is now infinity over infinity. Actually, negative infinity over infinity, which is fine. And we are going to get, actually, negative infinity over negative infinity, pardon me. When I apply L'Hopital's, I'm going to get 1 over x up top, and down below, I'm going to get negative 1 over x squared. Which gives us a negative x. And now when I plug in 0, we get that this limit is 0. Now, once again, I'm not done. Limit as x approaches 0 from the positive side becomes e to the ln x to the 2x. So this becomes e to the 0 power, which is 1. Last problem. Recall this is actually x to the 1 over x power, if you remember your exponent rules. And that is going to become, this one was the 0 to the 0. This one is going to become, as x goes to infinity, that's going to be infinity raised to the 0 power. So we're actually to our last type here. So this was infinity to the 0 power. So I'm going to apply the rule again. The same thing, this e to the ln. And once again, I'm just solely going to focus on the natural log exponent part. This becomes 1 over x, ln of x, or ln of x over x. And now I have infinity over infinity. So now I can apply L'Hopital's. That becomes 1 over x over 1 And now as that goes to infinity, the whole thing equals 1. Once again, I'm not done. I now need to go back to my original. This is 0, not 1. Pardon me. That goes to 0, so the whole thing becomes 0. And so this means that e to the ln of x to the 1 over x power becomes e to the 0, which once again is just 1. So we hit all the different indeterminate cases. And yeah, I hope that helps.